Hi, in this video we are going to train DC-Gan or deep convolutional GAN. In the previous vanilla GAN we have just used dense layers. In this one we are going to use convolutional layers, batch normalization layers and leaky ReLU layer. First of all, let's import what we need: TensorFlow, NumPy and Matplotlib, and make sure that you are connected to GPU. So in this video I'm going to connect to L4 GPU in order to train this GAN faster, but obviously you can train it on T4 GPU. Let's rerun it. And now these are some activation functions which are commonly used in deep learning. So this is our sigmoid activation function. We commonly used it with binary cross entropy on the last layer. And then this is the 10H activation function. So this could be used in the hidden layers or on the final layer. For example, if I normalize my dataset having pixel values between -1 and 1, then I'll use this 10H activation function on the last layer. But since our values are between 0 and 1, that's why we are going to use sigmoid. But in the upcoming videos, we will switch from sigmoid to 10H, because as you can see its values are from -1 to +1. Then this is the ReLU, and its values are between 0 and +infinity, so it converts all the negative values to the 0, and because of that conversion our gradients become 0, or learning process becomes 0 when our activations are negative. So that's why ReLU is not recommended in case of GANs for the hidden layers. Then we have leaky ReLU. So you can use leaky ReLU or CellU in the generator part of the GANs. And in this video, we are going to use this leaky ReLU. So it is bit like ReLU because the values on the positive axis ranges from 0 to +infinity, but it also deals with the negative values, even though it multiplies them with this alpha, which is 0.1, so it will reduce the magnitude of the negative value, but still we will have negative values as activations, and it help us train the model. Then we have this image which shows normalization techniques used in deep learning. We are going to use this batch norm, but latest research shows that batch norm is not very good normalization technique for GANs. That's why in the upcoming videos we will switch our gears from batch norm to layer norm. So it basically normalizes the data on the batch dimension. So here, as you can see, these images provides more information, and obviously I have got them from internet. These aren't generated by me. Now let's define our noise shape. It is going to be 32, and let's create our generator. So this is how the generator code is going to look like. First of all, since we are randomly sampling noise from the normal distribution, that's why the first layer is going to be dense layer, and it will transform that random noise into this shape 7 by 7 by 128. Then we have the leaky ReLU. As I told you, we are going to use leaky ReLU instead of ReLU, and I'm going to keep alpha to 0.2. Then we are going to reshape the activations we got from this leaky ReLU to 7 by 7 by 128. So after passing my activations from this reshape layer, the shape is going to be batch dimension into 7 into 7 into 128. Then I'm going to pass them from this convolutional layer, another leaky ReLU convolutional layer. So these are my layers, and now in this call method I'm going to pass my inputs from these layers one by one. So firstly dense layer, then reshape layer, then batch norm layer, and then activation layer. So if you read the literature, some people use activation first and then batch normalization, and some recommend that you should first batch normalize all the values and then use the activation. And then I'm going to use the transpose convolutional layer, the batch norm 2, and second ReLU activation function, and finally this third transpose convolutional layer. So the output from this convolutional layer is going to be batch size 28 by 28 by 1, as I have mentioned these strides and everything, so you can calculate it by your own, but final output will be this. Let's run. Now let's design the discriminator. In the discriminator, we are also going to use these convolutional layers. Since generator is going to generate image, that's why we have used here transpose convolutional layer. But discriminator is going to reduce our large complex image distribution into small column vector. That's why we are using here convolutional 2D. So again, firstly we are going to pass our image from the first convolutional layer, which is going to reduce the spatial dimension by half. So stride is 2 2. The output from this is going to be 14 by 14, and then we are passing here activation and then batch norm. So it's like the opposite of what we did in generator. And then I'm going to pass from another convolutional layer, so output from this will be 7 by 7, and then again activation batch norm, and then I'm going to flatten and final dense layer. So in final dense layer I have one unit with sigmoid activation function, so the output will be either 0 or 1. Then I'm going to combine them in the GAN class, so rest of the steps will remain the same. Let's create objects of each class. I'm going to pass some random noise from each object in order to see the number of trainable parameters. First, let's pass this random noise from the generator and then set generator.summary. So the generator size is this. Let's do the same process for discriminator. This generator is going to return me the image, and I'm going to pass that image as an input to the discriminator. So the purpose of basically doing this step is that when we will pass this random noise to the generator or this input image to the discriminator, TensorFlow is going to determine its input shape and will initialize all the weights and bias in these models so that we could see the actual size of these models. Let's do the same for GAN. So the total size of this whole DC-Gan is 627 at 42. It's around 2.4 MBs. Let's compile it, and this is my helper function, show images. This one is my train GAN step. So this is the exact code which we have written in the previous video. I have just copied it. Let's import our data. In this case, we are going to use fashion MNIST dataset instead of digit, but you can try it with digit as well. And again, we are going to reshape this X trend to like 28, 28, and 1, because in this case, we are going to use convolutional layers, and convolutional layer needs that channel dimension. So we are going to add that channel dimension to these images. Now I'll keep the batch size to 128, and then I'm going to shuffle it and batch my data. So if you're using T4 GPU, then make sure that you should keep this batch size to like 32 or maybe 16 in order to avoid that OOM or out of memory problem. But I hope in this case I'm not going to get that OOM. Available RAMs are 53 GB, so it's like more than enough for this training. Let's run. So I have trained like for 6 epochs, and these are the results of 6 epochs, although the training is still going on. So first of all, on the first epoch, you can see that results are like this. So these are my predicted images. In the second epoch, my results got better. Now we can see the shapes. This could be like a sandal, then these are some shorts, trousers, then shoes, another shoes. So things started making sense in the second epoch. Then in the third epoch, things become more prominent, so we can see the difference between this shoe and this shoe and these two shoes. The model is improving in each epoch. So this is the results of fourth epoch. Here results are more beautiful. So if you like train it for 20 epochs, obviously these results will be far better. But now I'm going to stop this training process because we can see that model is actually learning. So if you train for longer, it will be very good. So let's stop, and in the next video we are going to talk about another variant of GAN, and that is WGAN, and I'll see you there. Bye bye.